All right, this is the first lesson on parametrics and vectors, and we have two lessons on parametrics, vectors, and polars that will finish up all of our work for the year. Now, the reason why we only teach these in 2 days is because we're not introducing any new calculus here. We're just showing how to do everything you've learned to different types of equations. In this case, we'll do parametrically defined equations. And if you recall from pre-calculus, parametrically defined equations are where x and y are both driven by a third variable, usually t, which represents time. And so in this class, our t variable will be time. And typically speaking, your time will be restricted to greater than or equal to 0. Although I think in our first example here, we're not restricting it, just to show you a couple of things. So basically what happens is your x and y variables change as time changes. So let's see how I can do this using a slightly different recording system than normal today, so bear with me. So we have a parametric curve C, and we just generally use that variable C here, large cursive C, as a parametrically defined curve. Notice we're not calling it a function because many parametrically defined curves are not functions. And it's interesting because we can do calculus on non-functions using parametrics. So we have x equals t squared and y equals t cubed minus 3t. So let's just do a little pre-calc review and learn how to, or remember how to graph this parametrically defined curve. So if x equals t squared, then for these t values, we have first x equals 4, then 3, then 1, then 0, then 1, then 3, then 4. Y equals t cubed minus 3t, so I can plug in negative 2 here. I get out negative 8 plus 6 is negative 2. Plug in negative square root of 3, I'm going to get out negative 3 square root of 3 minus a negative 3 square root of 3. So I actually negate those and I'm left with 0. Plugging in a negative 1, I'm going to get negative 1 plus 3, which is 2. Plugging in a 0, I'm just going to get 0. Plugging in a 1, I'm going to get 1 minus 3, which is negative 2. Plugging in a 3, I get, plugging in a rad 3, I get 3 rad 3 minus 3 rad 3. So this goes to 0. And plugging in a 2, I'm going to have 8 minus 6, which is 2. So now we have our x and y values that are all driven by the independent variable time, and we're going to plot them on this grid. So let's go in ascending order of t. So we start at t equals negative 2, and the xy coordinate is 4, negative 2, right here. Then we go to 3, 0, we go to 1, 2, we go to 0, 0, 1, negative 2, 3, 0, and 4, 2. So the reason why it's important to graph these in the order of t, because we have to connect our dots in the order of t. So you see I start where t is negative and go towards where t is positive, and I get this curve. But I'm not actually done graphing this curve because I have to put the direction arrows in that tell us the order of ascending t, and these arrows are essential to completing your graph. So this is my parametrically defined curve, and as you can tell, it is not a function, which is, again, reiterating why we call it just C and not the parametrically defined function. It's just a parametrically defined curve. Okay, so let's start some calculus with this. Remember, we have x equals t squared, y equals t cubed minus 3t. And they're asking us here to find dx dt and dy dt. Well, we just have to differentiate each separate curve with respect to t. So x equals t squared goes to dx dt equals 2t. And then from the y, we have dy dt equals 3t squared minus 3. So those are basic power rules that we can apply. Because our independent variable is t and our dependent variable is x or y, we don't need any implicit differentiation or anything. It's just a straight up power rule. Then to find dy dx, what we have to do is divide dy dt by dx dt. So what's interesting is that dy dx, which doesn't have a t in it, it looks like we're just doing y with respect to x, which we are, but to get there we have to take dy dt divided by dx dt, which means we have 3t squared minus 3 divided by 2t. So dy dx is actually in terms of t. And that is very standard in parametrics, that you'll have your dy dx written in terms of t. So now they're asking us to find the second derivative. So dy dx is written in terms of t up here. This formula, we just need you to memorize. There is, if you go on Khan Academy or just Google it, you can find a derivation of why the second derivative with parametrics is like this, and it is a chain rule situation, but this is one of the very few things all year we just wave our hands at and say, please just know it, and I don't want to show you where it's coming from. So to get the second derivative, I will need a funky little situation here where I take the derivative of dy dx, and I'll do that using the quotient rule because I have a quotient. Then I'm going to divide by dx dt. So let's go ahead and do that. We're going to have the second derivative here is equal to, and I need the quotient rule, shall I sing? I'll have low d high, which is 6t, minus high, and then d low, square the bottom, which gives me 4t squared, and away we go. And then I'm going to divide all of that by my dx dt, which is 2t. And I'm definitely going to need to simplify here. So my second derivative is going to be, let's see, 12t squared minus 6t squared. And then I have a negative times a negative, so it'll be a positive 6 here. And then when I divide 4t squared by 2t, I get to 8t cubed. And when I clean this up just a little bit more, I'm going to get to 6t squared plus 6 over 8t cubed. And then it looks like I can just simplify this a bit more by dividing by 2 to get 3t squared plus 3 all over 4t cubed. That is my second derivative. So the key here is that you do have to memorize that when you differentiate to get the second derivative of a parametric, you do have to divide by dx dt.